Oof, happy Monday. How's everybody feeling? What's up, Hayden? What's up? What's up, Charlie? Beat RJ. Dude, RJ's changed, man. Have you guys noticed that, since the quarantine, RJ's not the same? He's changed. I miss RJBC. RJ before Corona. In the old world. Those were the days when I could count on RJ to hit me with a solid good morning. APRJBC. It's tough. It's tough adapting to all the changes. Mostly the changes with RJ, like grocery store changes, whatever. Sitting at home all day, whatever. But RJ not saying good morning, it's heartbreaking. Struggling again, man. Yo, someone toss Hayden their Ethernet cord. He needs to jack in. Help the kid out. Don't even know what to do with all these. Man, we got Ethernet cables everywhere here. Don't have enough ports. Well, just get your your Ethernet cable port hub. So it changes the one port into like 7, and you can just get them all. I think I just had a stroke reading that. That was the goal. Damn. Took you this long? Known you guys for like over a year now, and it took you all this time to finally get me? He's back. Well, Hayden, you could throw another good morning in and you'd still beat RJ. No more math teachers. That's step 1 that I'm running on. Ooh, uh-oh. Well, now we got some conflict. You're a commie, so. Wow. Harsh. All right. Let's go ahead and get into this. So, this is our third AP test review packet. I emailed you everything this morning. So I emailed you this Smart Notebook file. I should have emailed you the regular just packet blank packet itself, as well as the answer key. So should have all that good to go. So let's get into it. Right. Number one. So I have this table of values. Water is pumped into a tank at a rate modeled by W of T, liters per hour, for T between 0 and 8. Water is removed from the tank. That was bad. Let's try again. Modeled by R of T, which R of T is in this table here. R is differentiable and it's decreasing. That might be useful. And it gives us some specific values. And then finally, it tells us at T equals 0, so at the beginning, there's 50,000 liters of water in the tank. So, let's try some stuff out. Part A. Oh. Part A. Estimate R prime of 2. Show the work that leads to your answer. Indicate units of measure. All right, so our goal here, R prime of 2, but it says to estimate it. Right, so we are told what R is, right? R of T represents the amount of water that's being removed from the tank. And we have specific values. So at the beginning, there's 1,340 liters being removed per hour. After 1 hour, there's 1,190 liters being removed per hour, 950 per hour, 740 per hour, 700 per hour. Okay. So R prime of 2. Now, if I just had an equation for R, I would just take the derivative and then plug in 2. But that's not what we have, right? We have a table for R. So that makes sense then why it doesn't say find exactly, it says estimate. Okay. So hopefully we remember that if a derivative represents an instantaneous rate of change, right, the rate of change at that exact moment, right, if I want to, my next best step, if I want to estimate it, is to, instead of use an instantaneous rate of change, use an average rate of change. Okay, and average rate of change is, you might remember, is just like the slope formula, basically. Okay, so we want to estimate R prime of 2. Now, we don't have, especially since we don't have 2 on the table here, so I'm going to use my slope formula, and I'm going to use it for, not 1 and 3. Or sorry, not 0 and 3. But I'm going to use it with these 2 specific points of values, right? Since 2 is perfectly between 1 and 3, we'll do the average rate of change between 1 and 3. We'll take that as our estimate for 2, right? Kind of like with the Taylor polynomials, if we're trying to estimate something, I want to stay as close to I can around it. It'll give me a better estimate. Okay, so what I'm going to do is R of 3 minus R of 2 divided by 3 minus 2. Nope, not 2. Why am I doing 2? 1. Okay, so what actually is this? So on top, that would be 950 minus 1190. And the denominator, 3 minus 1. Okay. So that numerator, negative 240. 3 minus 1 is 2. So that would be negative 120. Okay, so r prime of 2 is approximately negative 120 liters per hour. Now we're estimating a derivative, so we're just going to use the table of values to do average rate of change. Whoa, good morning, RJ. Interesting. The internet must be running real slow today. Good to see you. Good to see you. "12 minutes late." Doesn't even show up with a pass. Can you believe this? Part B, use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. I was watching on my phone. You can still comment on your phone. Is this an overestimate or an underestimate of the total amount of water removed? Give a reason for your answer. All right, so first off, we want a left Riemann sum using 4 subintervals. Okay, so now this is like kind of like part A where we estimated a derivative using average rate of change. So now we're going to estimate an integral by doing a left Riemann sum. So if you remember, that's like where we actually draw the rectangles and we calculate the area of the rectangles, and that gives us an estimate of the area underneath the curve. Okay, so here's our 4 subintervals. All right, so we have a table of values. We're using a left one, so I know I'm going to use that left first point, and then this is my next point, this is my next point, and then this is my next point. We're also going to need, so we know the heights for each of these rectangles that we are going to draw. Hold on, let me erase this pink stuff so we can get it out of the way. Okay, so we're basically just estimating by using areas of rectangles. We know the heights of each rectangle, so the height of the first rectangle will be this, the height of the second rectangle will be this, third rectangle height, fourth rectangle height. Okay, and we won't use this last height of 700. If we were using a right Riemann sum, then we would have started with the 1, 3, 6, 8. Okay, but we're using a left one, so we use these 4. So now it's just, what is the base of each rectangle? Well, let's just look at how far between are. So between here and here, it's 1. Right, here to here, 1 to 3, that rectangle's base will be length 2. Here to here, that rectangle's base will be length 3. Okay, and then for my last rectangle, 6 to 8, it's a base of 2. Okay, so 1, 2, 3, 2 is how the bases go, and then I have all my heights there. So that first base is 1, right, times the height. So that first height, r of 0, is 1340. It's the area of my first rectangle. Second rectangle, the base will be 2 times the height, which is 1190. Third rectangle, the base length is 3 times the height, 950. Fourth rectangle, base 2, height is 740. And if I do this multiplication, add it all up, I get 8,050. So again, what this is an estimate for an integral, right? So if I look at r of t and integrate it, right, because we're talking about area under a curve, so that's what a Riemann sum does. From 0 to 8 is approximately 8,050 liters. Okay, so part A, estimate a derivative by using average rate of change. Part B, estimate an integral by using a Riemann sum, right, which is just adding up the areas of the rectangles. And we just have to be careful because it could ask us a left Riemann sum, it could ask us a right Riemann sum, it could ask us trapezoidal rule. Okay. But we're not done with part B. Okay. Now it's super easy that when we get here we forget and just kind of go on to the next thing. Remember this part. Right, it asks us, is this an overestimate or an underestimate? Okay, because we know it's an estimate in general. So the key here is going to be thinking about we know that r is decreasing, right? That was one of the pieces of information it told us. So let me sketch out okay, so let's say I have some function r that's decreasing. Right, and here's my 0, what is it? 1, 5, you know, whatever. I guess it doesn't matter. I'm just sketching here. But if we do a left Riemann sum, it's not a good picture. Let me do it like this so it's easier to see. All right, since we're doing a left Riemann sum, that means any rectangle that we make, the left point starts on the curve, and then the rectangle that we make goes over to the right. Right? Or for this next rectangle, the left side of the rectangle starts on the curve, and the rectangle goes for like this, okay? Or same thing, the left side of the rectangle starts on the curve, goes over, etc. Okay, so we should be able to visually see by this that this is going to be, oh, sorry. Here we go. Thank you. Okay, the left side of each rectangle starts on the curve and then extends to the right. So specifically since our function r is decreasing, like that green line that I drew is, now that's not exactly what it looks like, but it's decreasing. So that should tell us for our answer, this is an overestimate. Give a reason. How do we know? Since r of t is decreasing, and we are using a left Riemann sum. Okay. Now, but it's important that it has to be, the reason we can say overestimate is not just because it's decreasing or not just because it's a left Riemann sum, but combining these two things together means that we get the overestimate. But we have to think, depending on, because if it's decreasing but then a right Riemann sum, and then it'd be an then it would be an underestimate. But if it was increasing in a left Riemann sum or increasing in a right Riemann sum, okay, so it changes. So if it asks you a question like this, sketch out a little picture like this that helps you see what we're talking about, and it should be more easy to visualize. Okay, part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so I'm going to need to combine more information here. So let me get a fresh start. Total amount of water in the tank. So not the total amount being pumped in, not the total amount being pumped out, okay, or being removed, just the overall total. So I'm going to need to combine information about the two. Right, so another important piece, I know there's 50,000 liters at the start. Okay, so if I'm just kind of trying to build an equation here that represents how much water is in the tank, well, okay, I know I start with 50,000. Oops. Okay, so now if I think of how much water is, so starting with 50,000, now how much water is coming into the tank? Well, it's coming into the tank at this rate. Right, but I want to think about how much is going to get pumped in over a time of 0 to 8, right? It's from the beginning, 0 hours to 8 hours later. So how can I accumulate all of that together? Well, accumulation of rate of change is an integral. So plus the integral from 0 to 8, right? That'll tell me how much water is coming in. Right, or the total amount of water that comes in for the 8 hours. But then there's also a certain amount going out, right? So I'm going to subtract how much water is leaving. Well, like it says, use your answer from part B. We already found an estimate for how much water is leaving. So from part B, we said 8,050 liters. So minus 8,050. Right, that's exactly what we found for part B. Part B was total amount of water removed. So 50,000 represents the starting amounts. Integral of 0 to 8 of WT, or W of T, represents the total water in. 8,050 represents the total water out, or at least an estimate of it, which is fine. Right, and that equals the overall total of how much is there. That's not how you spell overall. Probably below my camera again. So this is something that I can just calculate. Right? I have everything I need here. I'm just going to type this into my calculator. Let me pull that up. Two network errors in one stream. Man, you're struggling, Hayden. Okay. So 50,000 plus the integral, so math 9, from 0 to 8 of, what is W of t, hold on, I forgot what that was. W of t was 2,000 to the, oops, 2,000 e to the power of negative, oops, there we go, negative t squared, or x squared, divided by 20. That's dx minus 8,050. Right, hopefully I typed this all in correctly. Yeah, that looks good. So my total is approximately, because again, this is still based on an estimate, so approximately 49,786. I think going back to my original, yeah, for part C, it tells me specifically to estimate to the nearest liter. So that's why I'm going to round those decimals here just to 49,786. Hayden, there's still plenty of time. What do you think we can get up to? Like 4 or 5 errors? Be unprecedented. But I do believe in you. All right, let's go for part D. For t between 0 and 8, is there a time t when the rate at which the water is pumped into the tank is the same as the water removed? Explain why or why not. Okay. So, is there a time where the rate in is the same as the rate out? Okay, that's what this is asking, and explain how we know. Resolution's gone out the window. There's 4 pixels on your screen. Right, this is what we're trying to figure out. Is there a time where these two rates would be the same? I got you. Okay, we're trying to figure this out. So another way that I can think about this, okay, is I want to kind of combine this all into one expression rather than on this side I have this equation and this side I have this equation. So another way that I could do this is say, well, that's the same thing as saying, is there a time where W of t minus R of t equals 0? Right, if I just subtract R of t from both sides. Right, I like it better that we have both of these all together in one expression. So I can just kind of consider this a new, just singular equation itself, right? This minus this. And I'm just trying to figure out, is there a time where this ever equals 0? Now we're not going to actually calculate what is the time that they equal 0. The question just asks, is there a time? So we are trying to prove that a time exists. Right? For this type of setup, we should probably be thinking of one of our theorems. Right? Potentially like intermediate value theorem or mean value theorem. Okay, those types of things. Now we have to remember the distinction between the two. Mean value theorem is about finding an average value. It's about finding a derivative. Okay, but we're not trying to find a specific derivative. Right? We're just trying to look at this expression, W of t minus R of t, and say, is there a value that exists? Okay. So, let's look at our expression. Let's look at the endpoints. Let's look at the beginning. So, the amount of water in at 0 minus, minus the water out at 0. Okay, R of t is 1340. That's just from the table. And W, so let me calculate again. So 2,000, oh wait, no, I don't need to do that. If I plug in 0, here, so this is just going to be e to the 0 power, which is just 1, so this would just be 2,000 for W. I'm smart. Right, so this equals whatever. I'm not really concerned about the specific value, but what I am concerned about is, hey, this would be larger than 0. Let me move the calculator again. Okay, now let me think about what would happen at the ends, right, or the other end specifically. So what about the amount of water in at 8 minus the amount of water out at 8? Okay, so for the amount of water in, if I just take W and plug in 8, so 2,000 E to the negative 8 squared divided by 20. So that's about 81.524. Right, that's just plugging in 8 for W. And then R, the amount of water out at 8 is 700. Okay, so again, I don't actually care what the value is, but what I do care, 81 minus 700 is going to give me a negative value. So I've done a couple important things here. I've shown that at the beginning, so at 0, the difference of those rates will be larger than 0. At 8, the difference of those rates will be less than 0. So I do need to first think, before I use my theorem, is W minus R continuous? Yes, it is. Okay, it tells me R is differentiable. Okay, W is continuous because it's just an exponential function is continuous. Right, there's no way we can get any asymptotes or anything like that, so we're fine. So that means W minus R will also be continuous. So what that means to us is we can then use the intermediate value theorem. So by the intermediate value theorem, there must be some yeah. There must be some t between 0 and 8 such that W of t, well, I guess initially what we proved, since we did the minus W minus R, so let's go through the full logic, which means W of t minus R of t equals 0, which then would mean that W of t equals R of t. Again, we showed at one end that our end result is greater than 0. We showed on the other side it's less than 0. So since I have something greater than 0, something less than 0, so in between there, at 0, which is what we're looking for because we're trying to prove, is there somewhere where these two rates are exactly the same, then we're able to do that by the intermediate value theorem. Did somebody put IVF? Yes. Was it me? Yes. I guess if you wanted to explain even more explicitly, we could. Which means the rate of water into the tank is the same as the rate it's removed. Okay, at that specific moment. Those two rates happen to be the same at that specific moment. There should be an apostrophe. Let's go on to question 2. On a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by G. So this is the amount of unprocessed gravel that arrives. T is between 0 and 8. So again, beginning of the workday, plant has 500 tons. All right, so that'll probably be important. It's a starting amount. All right, kind of like in the last problem, we started with 50,000 liters. Now we're starting with 500 tons of unprocessed gravel. During the hours of operation, the plant processes gravel at a constant rate of 100 tons per hour. Okay. So part A. Find G prime of 5. Using correct units, interpret your answer in the context of the problem. So not only find the derivative, but say, what the hell does this thing actually mean? What does this number represent? So let me bring up my calculator. All right, so turn it on. I'm going to go ahead and store that equation into my y1. So 45 cosine t squared over 18. Oops. Okay, I'm going to go ahead and store it in y1 because I'm going to need to use this equation, I think, a couple times in this problem. So rather than type, if I'm going to use my calculator where I need this equation multiple times, I'll go ahead and store it in y1. That way I can just use it there rather than typing in it again every single time. But it's up to you. So I have it in there that I can use it. Let me make sure. Okay, I'm in radians. Good. Okay, so first problem, G prime of 2. Or sorry, G prime of 5. So let's go to math. Is it 8? Yes, 8. So we're taking the derivative of x. Okay. So we want to pull up that y1. Okay, second. Oh, wait, oops, nope. Second trace is when we do like intercepts. Oops. Oh, shoot, I'm blanking out. How do we actually find those, the y1s and such? I truly don't remember. No, not trace. It's been so long since I've used it. Look, go away. I really can't remember. Oh, alpha trace. Neat. Cool, thanks. I knew it had the trace. That's why I mixed up the first. That's why I first went for second trace. I knew it was trace, but... And then we want to evaluate it at 5. That's what it asks us to do, G prime of 5. So here's that derivative. Negative 24.587 or 0.588. All right, since I think it tells us to round to 3 decimal places, so .588. Makes the decimal a little bigger. All right, but don't just stop there again, because this is talking about interpret. Tell me what this means. So G prime of 5. So the derivative of G. Well, first, what is G? G is the rate at which unprocessed gravel arrives. So I took a derivative of a rate. Right? So it's like the rate of the rate at which unprocessed gravel arrives. Okay, and so since it's negative, I know that what that means is G is decreasing. right? Or the rate is decreasing since this, so the rate at which unprocessed gravel arrives is decreasing by how much? By 24.588 tons. Now again, we did a derivative of a derivative. So the original G was already per hour. So this is tons per hour. Per hour. And when is this happening? Because that's not happening always, but it happens specifically when t equals 5 hours. Right, so we have this kind of weird wording because G was already a rate, so we took a derivative of a rate, so the rate of the rate, which is why we end up with this like per hour per hour. Right, this is already the units that regular G is in. So if we take the derivative of G, that's why we end up with this another per hour. Right, and so you'll notice I didn't put a negative sign in front of the 24. Right, but we indicate that by saying it's decreasing. Because it asked me to interpret it, so I want to explain the context that everything means. So that negative sign means that the rate of the rate is decreasing this specific amount per hour. Right, so the actual solving, G prime, that's pretty easy. It's just doing it in our calculator. Now the tough part comes from, can we actually explain what that means? Part B. Let's go back up. Find the total amount of unprocessed gravel that arrives at the plant during the hours of operation. So I know that's 0 to 8 because that's what it tells me on this workday. So I'm going to need to use multiple parts to create an expression that represents total. Right? Total that's arriving. Okay, well, G represents the amount arriving, or the rate of the amount arriving. So how do I decide, how do I go from a rate to how much is the actually accumulation of what is arriving? Well, we take an integral. So the integral of G, and what are the hours of operation? From 0 to 8. Okay, so we just have to get, so it's just this expression. So let me pull up my calculator. So integral math 9, 0 to 8 of, and again, we stored this, so alpha trace y1, great, dx 825.551. Sure. Tons of unprocessed gravel arriving.
during the normal hours of operation of the workday. We're given a rate, and we wanted to find an actual total of the things, so we take an integral, because integral takes an accumulation of change. All right, part C. Is the amount of unprocessed gravel at the plant, so amount of unprocessed gravel, is it increasing or decreasing at time t equals 5? Interesting. So let's show the work that leads to your answer. Okay, so now we're going to need some other information. So besides just using G, okay, so G is the amount of unprocessed gravel that's arriving, but how much gravel is actually there, right? And how much gravel is being processed, right? Well, we know it's being processed at 100 tons per hour. Okay, so my question is the amount that's coming in, is that more or less than the 100 that's going out? Right, since the question asks just is the amount increasing or decreasing, so, you know, however much there is, I don't really care, but I just care, is that amount going up or is it going down? Right? Are we building up unprocessed gravel because our processing is too slow, or are we able to get rid of the gravel, process it faster than it's coming in? All right, well, let's see. Well, let's figure out. I'll do it on the next page. And this asks specifically at t equals 5. So what is the rate at t equals 5? That's my first question. And more specifically, the rate in. Well, we can do that just by g of 5, right? G represents the rate coming in, so let's plug in 5 to it. I'll do that on my calculator as well. So I already have that equation stored, so I'm going to do alpha trace y1. And the way that we can tell this just to plug in 5 to the equation without doing an integral or derivative is we just use our parentheses format, so of 5. 98.1407. So again, to reiterate, the rate in at t equals 5, but the rate out at t equals 5, or I guess technically the rate out at any time, because the problem tells us the rate out is always 100. Okay. Well, the rate in is less than the rate out. Okay, so does that mean that the amount of gravel is increasing or decreasing? Right. So it should be decreasing because we're getting rid of the unprocessed gravel faster. We're processing it. It's going out faster than it's coming in. So, and then what did it tell us? What else did it tell us? A specific way to write or answer? Show the work that leads to your. Okay, so it just shows the work. So the amount of unprocessed gravel, that's not how you spell unprocessed. It's leaving faster than it's coming in. So that total amount, whatever it is going down. Okay, let's bring it home with part D. What is the maximum amount of unprocessed gravel at the plant during the hours of operation? Justify your answer. So, maximum amount of unprocessed gravel. All right, so I need to first, so again, that's what we're trying to find overall. Max amount of unprocessed gravel. Well, the first thing, before I find the maximum amount of that, I first need to say, okay, what is my expression that just represents the amount of gravel? Right, I know the amount of gravel that's coming in, right? The rate, I know the rate of the gravel coming in, I know the rate of the gravel going out, and I know how much gravel I started with. Okay, so let's do this like before. So let's just create let's just kind of use words to kind of create a formula. All right, so the amount of unprocessed gravel at the plant. We know it would be whatever the starting amount is, so however much there is at the start, okay, plus the amount total amount in minus the total amount out. Right? At any time t. So again, we have to think about at any moment. But the starting amount plus the total amount that's come in so far, and then subtract away the total amount that's gone out so far. All right, so this gives us a good kind of framework for what it is we're trying to do. If you're ever confused about, you need to make some equation or some expression, but you are like, I don't really know what the pieces should be, I would highly recommend doing something like this, where you create an equation that is just the ideas of the things you want. Right? Like, I think this makes much more sense as to what's going on, rather than if you're just thinking about the equations and like the actual specific values. This makes intuitive sense that, okay, how much is there at the start? Add to that however much is coming in, subtract to that however much has gone out. That should equal the amount that's there right now. Okay, and then build off of this. So now let's go through and actually create the equation. So let's call it A of t. So A of t, starting amount is 500. Problem told us that from the very beginning. All right, it has 500 of unprocessed gravel. Okay, plus, so total amount in minus total amount out. Now, this is not just using G, right? G by itself, because remember, G is the rate it's coming in. But I don't want the rate that it's coming in. I want the total accumulation of that in. So, accumulation we can represent by using an integral from 0 to, I'm not going to do 8. I'm just trying to create an equation that represents for any time, right? So from the starting amount to any time, right? So 0 to t. right? G of, I don't want to use t because we don't like to have the same variable here. So I'm just going to use like, you can use anything instead of here. You could use like S, you could use R, you could use P. If you want to use X, you could use X. It's whatever. I'm going to use S here. And I think that's what they do in the solutions key that I sent out as well. So I'll stay consistent with that. So G of S. So that integral would accumulate, since G is the rate it's coming in, so 0 to t integral would accumulate how much is coming in. But also, I'm going to kind of add on to this because I also want to accumulate how much is going out. So we know that it's just consistently 100 tons out per hour. All right, so I'll subtract 100. I'll put that in my integral as well, since I want to accumulate both things. I want to accumulate the amount in and the amount out. Okay, so this is an expression that represents the total amount of unprocessed gravel at the plant at any given time, right, at any t. Okay, so how do we find maxima? All right, I want to take this expression and I want to find a relative max. We can do, or I guess not even a relative max. I just want to find the max. All right, I want to find max. Where is max? Does anyone know? Has anyone talked to him? I'm worried about him. Okay. So find the max. Well, if I'm looking at an equation from a specific interval. So from 0 to 8, I want to find what is the absolute maximum of this. Then I'm thinking to myself, extreme value theorem. Okay, which is basically just like the first derivative test, right? Where we take the derivative, set it equal to 0, solve. Talked to him Saturday, but not since. Well, he could be anywhere by now, RJ. You got to keep track of this kid. So let's take the derivative. Derivative of 500, 0. All right, derivative of this thing. This should be the second fundamental theorem of calculus. So that means we take the expression, right? We're trying to take a derivative of an integral. So we'll take this expression, but plug in the upper bound. So g of t minus 100. And then we times that whole thing by the derivative of the upper bound. So that's just 1. So that's just all of this times 1. So that leaves it as is. And then that would be minus the expression again, but you plug in the lower bound, so g of 0 minus 100. But then, chain rule, you times that by the derivative of the lower bound. Well, the derivative of 0 is 0, so that would be times 0. Okay, so really, this part's useless. Okay, so this is our actual, well, right, this is our actual derivative we want to look at then. Right, and how do we find maximums or minimums? We take derivatives and we set them equal to 0. So equals 0. All right, g of t equals 100. So g of t is this expression. Oops. But I'm actually going to keep it here because, remember, on our calculators, can we tell our calculator, like, hey, find where this function equals this exact value? Not exactly, but we can tell our calculators, hey, find where this function equals 0. So if I now use this as my function, I can find where that equals 0. So let's pull up my calculator. So I'm going to go to my y equals, and so we could do two things here. I'm going to say, hey, y2 is actually just my first function minus 100. Right, so it's the same thing, 90 plus 45 cosine x squared over 18. So we could also just go up here and then scroll over and then do minus 100 here. That would work too. Or you could just create a second function based on the first one, but subtract 100, whatever. So let's graph this. It's looking pretty wild. Okay, but remember, we're only talking about from 0 to 8. So I'm going to make my window, let's just go 0 to 10 for my window. So this right here, this one to be outside my bounds. This right here is the point that I want. Where is this? This is where that expression will equal 0, which is what I'm looking for. So we can do second trace. Right, we want number 2, find the 0. So left bound, right bound. So just on either side of the x-intercept. Guess? Yeah, sure. 4.923. Okay, so we're still not done, but we're close. So what this is, if you remember, this is a critical point, right? We're using the extreme value theorem, and critical points either happen at the boundaries, right? Or the critical points happen wherever this derivative equals 0. So the maximum, the extreme value, can either happen on the ends, the boundaries, 0, 8, or it could happen at this critical point of 4.923. So let's just create a little table. So t, then a of t. So we have 0, the lower boundary, 4.923, and 8. Right? A of t, we have our expression for a of t. Right? We did that. So since we're running out of time, I won't go through and type all those in, but I have the values here anyways. But it would just be typing in this same expression into your calculator, except plug in 0 for t, plug in 4.923 for t, plug in 8. And here's the values we would get. If we plugged in 0, we'd get 500. Well, we don't even need to plug in 0. We know the amount at the beginning is 500. That's before any has started coming in or going out. Here would be 635.376. At time 8, we'd have 525.551. So now we look at these that we have for the amounts. Which one's the maximum? Right here. And so the question, did the question ask for the amount, or did the question ask when will the maximum amount happen? Because then it'll be a different answer. So it says, what is the max? Right? Not when will the max happen, but what is the maximum? So the max amount of unprocessed gravel at the plants is this many tons. Okay, and how do we know that? How do we figure that out? That was by the extreme value theorem. Wow. Let's try again. Okay. All right, so there's 1 and 2. Again, hey, go try some of 3 and 4 for tomorrow. At least maybe the setups or some ideas. Okay, got to practice getting these on your own, not just listening to me do them and say, I think that makes sense. Okay, be requesting PFAs, AFAs. Okay, again, reminder, I know there was some discrepancy about it earlier. Focus areas are completely open note. All right? But like I said, try to do them without, or at least try each problem without, but then if you don't feel comfortable, okay, go back and look at it with your notes, make sure you did that question correctly, and then move on to the next one. Okay. But let's get those done. I'm still deciding, I don't know, on our, I guess I'll probably make a very short, easy AFA instead of that last AFA sequences one. I think it's called or not the last one, but more convergence tests. So it's like integral test, nth term test, comparison test. I might just change that to like a Taylor polynomial AFA. That, or I'll just make it a lot of like easier questions where it's just, I don't know. But I'm still deciding, but I'm still going to figure that out. We'll see. Also, okay. So this is the one that I was talking about. Let me blow it up. More convergence tests. Nth term test is easy. It's just find his okay. Integral test is a little more complicated. Comparison test is a little more complicated. So I don't know. Maybe I'll just make this an nth term test and Taylor polynomial AFA. All right, not sure. But AP test prep, this is the AFA I'm talking about that has so much good stuff in it. Okay, there's a bunch of AB stuff. Right? There's full practice exams. I would highly recommend going through and doing those. Okay, and looking at your answers. I know you won't do multiple choice questions on your AP test, but still need to know how to do this stuff. Okay, BC. various FRQs from the last 3 actual AP tests. This is where those flashcards are that have every topic covered throughout BC. I'm looking for, I'm looking for some full-length practice tests to put in this one. Hopefully in the next couple days I'll find some good ones to put in there. I found some, but they're kind of just like, I don't know, they're not like actually made by AP College Board, so I want to make sure I'm actually putting good ones in there. AP formulas and need to know. The cram sheet, this is the one sheet that I talked about where it's like the stuff you need to know cold. Right, this is an excellent resource to use for studying, practicing, memorizing formulas, etc. These summaries are also good and are a little more in-depth rather than just formulas. So, but they don't have necessarily everything for BC, or at least this one doesn't. This one does, but it's very, very long. It's not very condensed. This is a good condensed, like front and back, boom, has all that stuff that you need. Okay, and again, this stuff is, if you were going into the AP test, I would say everything on this sheet, like the normal AP test, I would say everything on this sheet you need to know, like memorized. Okay, now, you have the luxury of not necessarily needing to do that, but it's still ideal. Because we just did 2 FRQs that took us an hour, 15 minutes. Right, your AP test is 2 FRQs and you have 40 minutes. Okay, now obviously you're not talking out loud and explaining every single step that you do, you're just doing it, but the point is it can still take a while. So don't expect to be able to look through your notes for a lot of things and, you know, check lots of stuff. You know, some stuff, but gotta know the stuff. Okay. Yeah, so I'm going over my time. Any questions for me? Hold on. Let me check here. I'm sure you guys have all requested. Oh, Rocky's going for sequences and series. I love it. No other requests here, but I'm happy to request them, or happy to approve them. Just let me know. Now we're talking. Here we go. All right. Otherwise, I'll see you guys tomorrow. We'll do those next 2 problems. And yeah. All right. Have a great rest. Oh my gosh. And another one. This is amazing. I don't know that the entire semester we've had 3 people attempting a PFA at the same time. This is unprecedented. Okay. All right. Good luck, guys. And I'll see you tomorrow. Have a great rest of your